shear buckling design methods, in which the second method is tension field method. The tension field method based on the post shear buckling strength may be used for webs with intermediate transfer stiffener in addition to the transfer stiffness at the supports, provided the panels adjacent to the panel under tension field action or the end posts provide anchorage for the tension fields, and if C by D is greater than or equal to 1, where C is spacing of transfer stiffener and D is depth of the web. The nominal shear capacity Vn is given as Vtf shear strength in tension field method, and design shear capacity is given as Vn by gamma m naught, where gamma m naught is equal to 1.1. First is the width of the tension field. The marked length is width of tension field Wtf. Let us say this is St and this is Sc. Since this is compression flange, so the anchorage length in the compression flange is indicated as Sc, and since this is a tension flange, the anchorage length in the tension flange is indicated as St. This is spacing of transfer stiffness C, and this is the depth of the web. Let us say this angle is phi, then this will also be phi. It is 90 degrees here and 90 here. So then this width will be equal to St into sin phi, and here this width will be equal to Sc into sin phi, and taking it separately, this is C, this is phi, and this will be 90 degrees. Then here to here this distance will be C into sin phi. If this is phi and this is 90, this will be 90 minus phi, and this angle will be phi again. Since the overall depth of the web is D, then distance from here to here will be equal to, from this right angle triangle, it is D into cos phi. So subtracting both, this width will be obtained, that is equal to D into cos phi minus C into sin phi. So from this width of tension field WTF will be equal to the St sin phi plus the inner width, that is D into cos phi minus C sin phi plus the Sc into sin phi. This can further be modified as D into cos phi minus, taking sin phi as common, it will be C minus Sc minus St into sin phi, where phi will be equal to tan inverse of D by C by 1.5, and phi is inclination of the tension field. So phi is inclination of tension field. Knowing WTF, width of tension field, Vn, that is equal to Vtf. So Vtf is given as VCR plus 0.9 times of, that is 90% increase, into area, that is width of tension field, into thickness of the web, into stress, that is Fv into sin phi, and this value should always be less than or equal to Vp, that is pure shear condition, that is should be less than or equal to Av into FIW by root 3, where VCR is Av into tau b. In this formula, Fv is yield strength of the tension field and it is given as Fv, which is equal to under root of FIW square minus 3 times of tau b square plus phi square minus phi, where phi is 1.5 times of tau b into sine 2 phi, where psi is this one, and we already know phi is tan inverse of d by c by 1.5, and tau b is already defined. It is shear stress corresponding to web buckling and it is given as tau b, which is equal to FIW by root 3 if lambda w is less than or equal to 0.8, and tau b is given as, this is root 3, tau b is given as 1 minus 0.8 times of lambda w minus 0.8 into FIW by root 3 for lambda w between 0.8 and 1.2, whereas tau b is given as FIW by root 3 times of lambda w square for lambda w greater than or equal to 1.2, where lambda w is non-dimensional slenderness ratio for web buckling strength, which is given as under root of FIW by root 3 into tau CRE, where tau CRE is elastic critical shear stress, which is equal to kV into pi square into E by 12 times of 1 minus mu square, where mu is Poisson's ratio, into d by Tw whole square, where kV is 5.35 for when transverse stiffeners are not provided. Stiffeners are not provided, it supports provided only at supports, and this kV is given as 4 plus 5.35 by c by d whole square for c by d less than 1, and whereas it is given as 5.35 plus 4 by c by d whole square for c by d greater than or equal to 1. Knowing tau b, we can substitute it here and find psi and substitute and find Fv. Knowing Fv, we can substitute it here. Now to find S, this is Sc and this is St. This is compression flange and these are plastic hinges. Say the stiffener spacing is C and overall depth is D, and these are the transverse stiffeners. We know this angle is phi and this is FYW, that is yield strength of web. Then considering a strip in which this is SC, then when this is phi, then this component will be SC into sine phi, and the thickness of this will be thickness of the web, since in this direction FIW yield strength of web, in which this is tension field stress at yield, and this is the yield zone. We know MFR is moment is ZP into Fy, in which ZP is BD square by 4 for rectangle. So this cross section is in this form, wherein the height is S into sin phi and the thickness is TW. So along this axis ZP will be equal to TW into S into sin phi whole square by 4. So substituting, ZP is TW into S into sin phi whole square by 4 into FIW, which is equal to MFR. From this we can find S, where S is equal to SC, which is equal to ST, which are anchorage lengths of tension field along compression and tension flanges. From this, MFR will be equal to TW into S square into sin square phi by 4 into FIW. From this, S will be equal to 2 by sin phi into under root of MFR by TW into FR. So the S formula is S is same as SC, which is same as ST, which is equal to 2 by sin phi into under root of MFR by TW into FR, and this S should always be less than or equal to C, transverse spacing between the stiffeners. In this, MFR is the reduced plastic moment capacity of the respective flanges of the respective flange plate, disregarding any edge stiffeners after accounting for the axial force, which is indicated as NF in the flanges due to overall bending and any external axial force in the cross section, and MFR is given as breadth of the flange into thickness of the flange square by 4. So this is ZP into Fy is given as FYF into 1 minus NF by breadth of the flange into thickness of the flange is the area into stress is FYF, that is yield strength of flange, by gamma m naught whole square, in which BF and TF are width and thickness of the relevant flange, and FYF is yield stress of the flange.